All right, chemistry kiddos, we are going to have a quick, just the basics lesson on oxidation reduction because I kind of realized that the guided notes PowerPoint needs to be edited, and you know, some people's heads were swimming yesterday while we were going through this. So I just want to do a quick video on the basics, what you need to know about redox, and then again show you an example on how to balance one of these oxidation reduction reactions that take place in a acidic or basic solution. Okay, but I have to stress this: you have to look at the notes that I give you. You have to check out the notes and read them and try to comprehend to the best of your ability, not just look at them and get an idea. You need to actually try to figure out what the notes are telling you and learn from them. And then if you don't get it, you got to come in and ask questions. Now, I covered in class, but we have to go fast in class. So it may not be covered as quickly or as slowly or as many examples as you need. And that's why you need to look at the notes and try to figure it out for yourself as well. So the notes I'm referring to for oxidation reduction, there's two sets. One is the steps for how to balance it in an acidic or basic solution. But the more important ones that you really need to just take in and understand, and what we covered last class are these notes. Okay, so the notes for assigning oxidation states. You have to be able to look at a compound and go, okay, this is +1, that's -1. This is +1, oxygen's -2, and that's going to make the sulfur +6, right? You have to look at this +2, -1. You got to look at this and say, okay, calcium's +2, oxygen's -2, and the phosphorus has to be +5 in this case. Like, we have to do that. You have to remember this exception, okay? And really, it's hydrogen peroxide. In hydrogen peroxide, you got to remember oxygen's -1. Okay, make sure you know that. Don't fall for that. Okay, and so you have to be able to assign oxidation states. Okay, if we can't assign oxidation states, then this doesn't make this. It won't make any sense to you at all. So that's the first thing. So make sure you read over those notes. Google how to assign oxidation states, or YouTube and watch a video, or come ask me questions if you still don't get it. So it's not going to work unless you can do that. All right. So let's start. Let's talk about the basics. All right. So redox stands for oxidation reduction. Right. It's just a short little acronym. It stands for oxidation reduction, and it's a type of reaction. Okay. So it's just another way to classify chemical reactions. Right. So I can classify chemical reaction as double replacement. I could classify it as single replacement, synthesis, decomposition, combustion, whatever. I could do all these different types of classifications, and another one now is oxidation reduction, redox, okay? And so what it is a reaction that involves an exchange of electrons. Something oxidizes, which means lose electrons. Something reduces, which means gains electrons. So whatever loses electrons is giving their electrons up to whatever gains the electrons, and that gets reduced. So whatever gets oxidized is reducing something else, or whatever is getting reduced is taking electrons away from whatever's being oxidized. It depends on how you want to look at it, but that's the idea. There's an exchange of electrons, and any reaction that is a result of any exchange of electrons can be classified as redox, oxidation reduction. Okay? So why do we call gaining electrons reduction? Because the charge reduces as you gain electrons. So what is reducing when you gain electrons? The charge. Okay. Oxidation just means you've lost electrons. What is that going to do to your overall charge? It's going to increase. Okay. All right. So again, redox involves the transfer of electrons. Okay. What is being oxidized is transferring its electrons to what is being reduced. Way to remember what oxidation means versus what reduction means. You can either remember Leo the lion says grr, okay, or oil rig. Okay, so lose electrons oxidation, gain electrons reduction, or you could think oxidation is losing, reduction is gaining in It's all about the electrons. Okay. All right. So to tell what gets oxidized and what gets reduced in a redox reaction, we have to assign oxidation states, okay, or oxidation numbers, right? So that's this. We got to know how to do it. Assigning oxidation states. You can say oxidation state, you can say oxidation number is the same thing, okay? All right. So the really kind of basic rules that we want to follow are if it's an element, it's zero. If it's just a monatomic ion, it's just whatever the charge of the ion is. And then everything else is really based on electronegativity. The more electronegative atom is going to get a normal negative charge, its normal negative charge. And then everything else has to follow this rule, okay? All oxidation numbers must add up to the overall charge. All oxidation numbers must add up to the overall charge. So we'll go over some examples, but let's look at some of the rules. All right, so this is kind of just a brief, this is kind of a simplification of the rules on this handout here, okay? So O is usually going to get a -2, and that's because oxygen is the second most electronegative element. So usually oxygen is going to be the most electronegative element in a compound, and therefore get its normal -2 charge. Hydrogen is usually going to be +1. It could be a -1 if it's paired up with a metal, but hydrogen is going to be +1. And understand that hydrogen cannot be anything greater than +1 because all hydrogen is a proton, all right? So some exceptions. Oxygen is -1 in hydrogen peroxide. So when you see this compound, you got to remember oxygen's -1. If you made oxygen a -2, that would make hydrogen a +2. And remember, we just went over hydrogen can't be greater than +1 because it's just a proton. All right. And then if oxygen's paired up with fluorine for some reason, like in this compound, it can't have the negative charge because it's not more electronegative than fluorine. So fluorine would get the -1 charge, and that would make oxygen in this compound +2. Okay. And then again, hydrogen is normally in a compound going to be +1, but if it's paired up with a metal, then it will be an anion, and the metal will be a cation. So this will be hydrogen as a -1 if it's paired up with a metal. Okay. All right, so again, remember this rule. All oxidation numbers must add up to the overall charge. So let's go with an example. Here's benzene. We want to assign oxidation numbers to the carbon and the hydrogen. Notice that there is no charge to this compound. Its net charge is 0, okay? So we would give +1 to the hydrogen, right? That's our general rule for hydrogen, unless it's paired up with a metal, but it's not paired up with a metal in this case. It's paired up with a non-metal carbon. So +1 for the hydrogen. Now, you have 6 hydrogens. So that's a total of +6. So the total for the carbon has to be -6, but you have 6 of them. So that means each carbon is -1. All right. So if you were asked to assign the oxidation states for the elements in benzene, hydrogen would be +1 and carbon would be -1. Okay. So let's do an ion like permanganate. Okay. So this is not a monatomic ion. This is one of our polyatomic ions. So it's got manganese and oxygen. So if I want to assign the oxidation states to each atom here, I have to understand that the overall charge is now -1. So all the oxidation numbers have to add up to -1. Okay, well, we would give oxygen, which is the most electronegative element in this compound or in this ion, we would give it a -2. But you have 4 of them. So -2 times 4, that's a total of -8. Okay. So to add up to -1, manganese would have to be +7. +7 plus a -8 would equal -1. And since you only have 1 manganese, that means that charge of the manganese or that oxidation state of the manganese is +7. Okay. So in permanganate, manganese is +7 and oxygen is -2. Okay. All right. So the questions you want to be able to answer is a chemical reaction also a redox reaction? Is it also oxidation reduction? What is being oxidized in the reaction? What is being reduced? And sometimes you'll be asked this: what is the oxidizing agent? What is the reducing agent? When you see that word agent, think opposite. So I'll say this and I'll say it again, but whatever is reduced is the oxidizing agent. So what gets reduced is the oxidizing agent. whatever gets oxidized is the reducing agent. So whatever loses electrons ends up being the reducing agent. Whatever gains electrons ends up being the oxidizing agent. Okay. All right. So let's look at this reaction. This is just a double replacement reaction, and we want to know if it's redox or not. And if it is redox, what's being oxidized, what's being reduced, what's the oxidizing agent, what's the reducing agent, right? That we want to be able to answer all of these questions. Okay. So what we would do here is assign oxidation states. So this is what we would do. And again, if you don't understand how I did this, you need to figure that out, okay? Sodium's +1 because it's a monatomic ion. Oxygen would be -2. And to make this whole thing add up to 0, nitrogen would have to be +5. Okay, silver's +1, that's -1, +1, -1, +1, +5, -2. So what we'll notice is sodium's oxidation number stayed the same. Nitrogen's oxidation number stayed the same. Oxygen's oxidation number stayed the same. Silver's oxidation number, stayed the same. And chlorine's oxidation number stayed the same. So no oxidation numbers changed. This is not a redox reaction. And what you'll find is most double replacement reactions are also non-redox. Okay. All right, so that's not a redox reaction. So nothing got oxidized, nothing got reduced. Nothing is the oxidizing agent, and nothing is the reducing agent there. Right? But what about this one? Okay. Sulfur plus oxygen yields sulfur trioxide. Well, let's assign oxidation states. Remember, this is an element, so 0. This is an element, so 0. Okay? This is a compound, so not 0, but let's find out. Oxygen's more electronegative, so we would give it a -2. But you have 3 of them, so that's a total of -6. So that means the sulfur has to be +6. So we would assign our oxidation states. And the oxidation numbers did change. So yes, it is redox. This is an oxidation reduction reaction. Okay. Sulfur went from 0 to +6, and oxygen went from 0 to -2. All right. So going from 0 to +6, that's an increase in charge or oxidation number, which means you lost electrons, right? To go from 0 to +6, you have to lose negative charge. So you lost electrons. Okay. Sulfur is oxidized. So yes, it's redox, and sulfur is oxidized. Okay. O went from 0 to -2. Its charge reduced, it decreased. That means it gained electrons. So oxygen was reduced. So in this redox reaction, sulfur was oxidized, oxygen was reduced. Okay. But then remember, agent is opposite. So since sulfur was oxidized, sulfur would be called the reducing agent. And since oxygen was reduced, oxygen would be called the since oxygen was reduced, oxygen would be called the oxidizing agent. Okay. All right. So, I mean, those are really the basics for redox. Now let's talk about half reactions. Okay. So half reactions kind of show us the oxidation portion of the reaction and the reduction portion. So we take a redox reaction, which is oxidation reduction, and we separate it into the oxidation portion and the reduction portion. So we have the oxidation half and the reduction half. Okay, so let's say this reaction takes place in an acidic solution, okay, and we want to balance it using the half reaction method, right? The first thing is to, and this is an oxygen, by the way, sorry for the bad handwriting. So this is H2C2O4, all right? So we would assign oxidation states. All right, and so we would notice that manganese goes from +7 to +2, so that is reduction. So manganese is reduced, and we'll notice that the oxygen stayed the same. There's no hydrogen on this side, but the carbon increased. It went from +3 to +4, so that's oxidation. So notice that the carbon is oxidized, and so if I wanted to write the oxidation half reaction, I would write carbon in whatever carbon was in, and yields whatever it turned into. So this would be the oxidation portion of my half reaction, okay? Of the oxidation half reaction. And then manganese got reduced, so we would take manganese, the source of the manganese, which is the permanganate ion, and yields whatever it turned into. So this would be the reduction half reaction right here. Okay. Now, obviously, these aren't balanced, but this is how we would start off our oxidation half. This is how we would start off our reduction half. So now, if we're following our steps for balancing our half reactions in an acidic solution, the next step is So let's just look at the oxidation half. The next step is making sure we balance anything that's not hydrogen or oxygen. So we have to balance the carbon. And right now, the way this equation looks like up here, I have 2 carbons, but I only have 1 carbon here. So that's why I put a 2 here. So I put a 2 there to balance the carbons. The very next step is to balance the oxygen by adding water. Okay, now do we need to balance the oxygen? I have 4 oxygens here, I put a 2 here, and now I have 4 oxygens on this side. So I don't need to add water because the oxygen is balanced on each side. Okay, so we balance the carbon, then we balance the oxygen by adding water. We didn't need to do that because we have 4 on this side and 4 on this side. Now we balance any hydrogen by adding H+. So we have 2 H's, so I needed to add 2 H+. So all the matter is balanced. The hydrogen's balanced, the carbon's balanced, the oxygen's balanced. But now we need to balance the charge, and we do that by adding electrons. And a thing to remember is if you know that this is an oxidation half reaction, you should be expecting to put electrons on this side because oxidation produces electrons, okay? So the overall charge without these 2 electrons here, if we just look at this stuff right here, we have a 2 plus and 2 zeros. So the overall charge on this side is +2. The overall charge on this side is 0. So we add 2 electrons to bring this side down to 0 to match that side. So 2 electrons. And this should make sense. Let's think about it. Okay, what are we saying carbon's doing here? Carbon's going from +3 to +4. To go from +3 to +4, a carbon atom has to lose 1 electron. But we have 2 carbons doing it. 2 carbons are going from +3 to +4. So that would produce 2 electrons, and there they are. Okay, so now let's look at the, reduction half reaction. Okay, so again, the first step is to balance the manganese. Okay, well, manganese is balanced, so I don't need to do anything. Then we balance the oxygen by adding water. Okay, so 4 oxygens, I had to add 4 waters over here to get 4 oxygens. Now we balance the hydrogen by adding H+. By putting 4 waters over here, I have 8 hydrogens, so I got to put 8 H+s on this side. Okay, so now I balance the H+. All right, now we balance the charge. Now remember, this was a reduction half reaction, so we should be expecting to put electrons on this side of the equation, okay? Because electrons are required, they are a reactant for reduction, okay? So let's ignore those electrons for now. If we look at these things right here, we have 8 plus and -1, so we have a +7 on this side, and we have a total of +2 on this side. So to bring a +7 down to a +2, we have to add 5 electrons, okay? And again, let's think about it in terms of oxidation state, right? What are we saying? Manganese is going from +7 to +2. How does a manganese go from a +7 to a +2? It's got to gain 5 electrons. And so we have 1 manganese going from +7 to +2. That's going to require 5 electrons. There we go. All right. Now, if I want to add the 2 equations together, the problem is I have to have the equal number of electrons being transferred, right? The electrons that get produced have to equal the electrons that are required for the reduction half. And right now they're not. I have 2 electrons being produced and I have 5 electrons being used. So what we have to do is we would multiply this reaction by 5. So if I multiplied this, I would get 5 of these, 10 of these, 10 of these, and 10 electrons. And I would multiply this reaction by 2. And if I multiplied this reaction by 2, it would be 10 electrons, 16 H pluses, 2 permanganates, 2 manganese, and 8 waters, right? So I'm going to multiply through by 5 here. I'm going to multiply through by 2 here, okay? So here is my oxidation half reaction multiplied by 5. And here's my reduction reaction multiplied by 2, okay? So the electrons completely cancel, but let's notice that that's not the only thing that cancels. I have 10 H pluses here and I have 16 H pluses here. So this 10 H pluses will go away and this 16 will become a 6, okay? And sometimes waters will cancel. That doesn't happen in this case, but sometimes you might have some waters that cancel. But that's no water cancels in this case, all right? So then we just add everything, all right? We have 6 of these plus 5 of those plus 2 of these, everything on the left side of the arrow, and then everything on the right side of the arrow. So this would be our balanced reaction. And really, it's kind of difficult to figure this balanced half reaction, to figure this balanced half reaction if you were just given this, right? We were just given, where was it? We were just given this. And so it's kind of hard to come up with that equation if you're not doing the half reaction method, right? So you have to do the half reaction method to come up with that. Because if you notice that the reaction that I gave you initially didn't have any H plus in it, didn't have any water in it. So how would you know? Okay? So you have to sit there. You know that water's available because it's an aqueous solution. And you know that H plus is available because it's an acidic solution. But how would you know where to put it? Well, you got to do the half reaction method. All right? So hopefully that helped you. Maybe it reinforced what we talked about last class and helps you understand it a little bit better. Keep working. You got that book work to work on. And so thanks for watching. Like and subscribe. Like and subscribe. Smash that like button. Have a great day.